Hello everybody, I'm Nick, and in this video I'm going to show you why you are probably using the wrong LINQ method for a specific operation in C# and how by using the right one you're going to reduce the performance of said operation in half, but also something very interesting. This video was supposed to be a code cop, part of my series where I go through LinkedIn posts that suggest questionable advice and I try to correct it, and even though this advice is not necessarily the best one, what really piqued my interest is that the author, but also the comments, did not understand why these two methods perform differently, even though they look very similar. So in this video, I'm not only going to show you a new way to do a specific thing using LINQ or actually a method of some enumerables, but also kind of teach you how you can identify why certain behavior works in a certain way in C# and how you can debug it and understand how it actually works behind the scenes. This is a very important skill, especially when you try to debug or troubleshoot both normal behavior but also performance. If you like that type of content and you want to see more, make sure you subscribe. For more training, check out my courses on domtrain.com. Okay, so let me show what I have here. I'm going to go straight to the point. I'm going to show you exactly the two methods that we're going to be comparing. So these methods have to do with enumerables, and more specifically they apply to lists, arrays, and immutable lists. And it is the following. Assume we have some numbers over here, so I'm going to create a new list, and actually why not use the new feature where we can just have collections like this. So I'm going to say numbers, and then I'm going to say just 1, 2, and 3. So something like that. Now let's say I want to see if all of them are positive. How would you do that? Well, you really have two options, but the most common one you probably have seen is the following. You would say numbers.all, and you have a predicate in here where you say all are more than 0, and that is it. And in fact, if you go ahead and you say console.writeLine and I quickly print the value, you'll see that in fact we are getting true. Now, if I had a negative value over here and I run this, as you're going to see, we're going to get false. That's basically it. You want to make sure that all items in a collection match specific criteria, and that criteria is passed in the form of a predicate. Now, many people don't know this, but there's actually another method that lists, arrays, immutable lists also have that allow you to do the same matching. And on the surface level, it looks exactly the same. In fact, I can change this all to true for all, and nothing changes in my code, and the behavior is exactly the same. These two methods will have the exact same matching criteria, and they both accept a predicate. So if I run this application again, I'm going to get false, and if I run this again, I'm going to get true. However, what's very interesting about these two approaches, even though they look very similar, is that true for all will perform twice as fast as all. Let's see that. I'm going to delete that and I'm going to go and say benchmark runner.run benchmarks. And I've already created benchmarks for these two operations. So what I have over here is 10,000 numbers. All of them are using the same seed, so the same sequence will be generated. They are always going to be positive, and they're passed into a list, as you can see over here. And then all I'm saying is all of them are positive or true for all. And this will be the best example we have to identify the performance of the two, because it means that we're gonna go through every single one of those items, in this case 10,000, and I want a bigger range so we have a better representation of how these two things scale. So if I make sure that this is in release mode and I go and I say run, let's run these benchmarks and see how they do compare. Now, before I move on, I'd like to let you know that we just launched a brand new course on DomTrain called Getting Started with Microservice Architecture, and that course is authored by AWS solution architect James Istam. It will teach you everything you need to know to get started with microservices the right way by someone who works for freaking AWS. Like, that's all they do. They know a thing or two, to say the least, and I'm so happy to have him author this course on DomTrain because it is just fantastic and it's going to set the right foundation for all of you. So to celebrate the launch of that course, check the link in the description and use code MICRO20 to claim a 20% discount. This is only valid for the first 500 of you, and those 500 of you will also get a special 40% discount later when the deep dive is out. This is a really unique opportunity, so please don't miss it. Now back to the video. Okay, so results are back and let's see what we have here. So as you can see, the all method, 11 microseconds and 40 bytes of memory. True for all, the exact same signature, mind you, 6 microseconds, 6.3, and no memory allocated at all. So on the surface level, the advice is use true for all overall whenever you can. So arrays, lists, and immutable lists. But the question I want to answer really is why these two things perform differently. So if we go inside those methods, you're going to see that one of them is an extension on the IEnumerable, very important, and then it's for eaching over every item, and then it checks with the predicate. So if the predicate matches using the element or it doesn't match, then return false, otherwise return true. And you're going to see that the predicate here is a function that accepts the t source item and returns a boolean. Now, if I go to the true for all one, this is a method in this case on the list. So it is sort of optimized for lists by default. And it uses a predicate, which the predicate of t is basically the same as a function of t that returns a boolean. You can treat it as the exact same thing. That's why the usage of it is basically exactly the same. The difference is there is one less null check, which doesn't really make much of a difference, unless, of course, for when you go into the throwing part. But in this case, this will be false. But what we have here is a for loop, not a for each loop. And surprisingly, or maybe unsurprisingly for many of you, that's what makes the difference. What I want to do is pull out those methods from those extensions or local list methods and try to take a deeper look as to why it's happening. So both the all method is now extracted and the true for all. And for argument's sake, just to make sure that there is no foul play in me extracting them and the behavior changing, I know it won't change, but I want you to know that as well. So I'm going to quickly just change this and rerun the benchmarks just so you can see that we're going to have the exact same performance. So 11.3 and 6.2 or 6.3 roughly. So this changed and this changed. Let me quickly run the benchmarks for you. It's going to be just that and you're going to see the results. Okay, so results are back. As you can see, 11.1, 6.3, again, within the potential margin of error, but it is basically the same thing. So this allows us to now take a deeper look with having control and access to the code so we can easily debug it. The for loop, there is not much really to take a look at. And what I've done here is I've actually calculated the size only once outside of the for loop, which will give it a better chance in how it is going to perform. But that's very, very slight as well. It doesn't really make much of a difference. The biggest difference here is on this for each loop, and I'm going to explain why. What I'm going to do is I'm going to use the IL viewer of Rider, and I'm going to show you the low-level C#. So let me just move myself out of the way. And what I want you to see is that this for each loop over here will be turned into this block over here. Because what's going to happen is the enumerator of that IEnumerable will be used here, and it's going to be sort of unraveled or unwrapped into this while loop where you have while move next, get the current item, check the predicate, and go on. And the biggest issue of this whole thing is, of course, you have a dispose method that's going to be called over here, but also the IEnumerator. And the reason why this is a problem is because this enumerator will be allocated. Those are the 40 bytes you are seeing. How do I know this? Well, because if I convert this to the unwrapped version, which will look exactly like this, which it's very nice that Rider will tell me that this must be disposed as well. But what I can do now is I can put a breakpoint here. I can go to program.cs, change this to debug mode, and then call the method from here. So if I add a breakpoint here, turn this into debug, run it, what you're going to see is the memory of the application. So I'm going to step into that, and I'm going to go all the way up to this breakpoint. Now at this point, I'm going to go here and I'm going to say, go to the memory and load all the classes. And you're going to see that we have the memory of the application at this point. And you can also see how many bytes are allocated here. So if I say step over this enumerator now, I can see the type of the enumerator, and it is of type enumerator of the list, which by the way exists within this class over here. That's the struct of the enumerator. So it is now created. But if I say load classes, as you're going to see, I have 40 new bytes. And if you remember, those are the 40 bytes that I saw on the benchmark results over here. So it's the enumerator being allocated, is the disposal, and there's a few method calls that ultimately lead to this performance being twice as slow. Now, can we actually optimize this? Technically, we can, and I'm not going to bore you with the specifics on this. So if you want to grab the code for this, you can use the link in the description. I'm not really going to show it here. But what I did is I added this struct enumerator over here that is a custom implementation. And what this allows me to do is create my own list type. And I can specify that list type to use that enumerator instead. And that you can see over here. So I have my list type using a real list behind the scenes. I expose some of the methods to a forwarding, and then I'm using that custom enumerator that I just made. So if I go here, I can say, hey, here's my list, and I'm going to add a few numbers to that list, and then I can take that list and I can run benchmarks against it. Let's go ahead and update the benchmark method over here, or class, sorry, and add the benchmark for that new my list using my custom enumerator. So what I'm going to say is my numbers over here using my list. And then I'm just going to quickly copy everything from the main list to the my numbers list. So they have the exact same values basically. Then all I'm going to do is add an all method for my list. So it accepts my list as a type. The rest is exactly the same, and I still have a for each loop over here. However, because I have my custom enumeration type over here, as you're going to see in the IL viewer, if I go lower, and in fact, I have to say build this thing as well, which it doesn't build because I need something in my program.cs. Let's go ahead and add this, go back here, run this, or sorry, not run, but build. And if I go to the for each, you're going to see that the enumerator is now this struct custom enumerator being used. And why does that make a difference? Well, let's go ahead and add a benchmark over here with basically the exact same signature, but all my list instead. I'm going to use all my lists here, past the source, which is my numbers. The rest is still the same. So let's go ahead and turn this into release mode and run it and see how now the three compare. All right, so results are back, and let's see now what we have. And as you can see now, the for each loop is performing exactly the same as the for loop without any more allocations and the basically exact same speed and execution time. So as you can see now, the issue is clear. It is an enumeration, it is the allocation, and of course the extra stuff that happened behind the scenes, including the disposal, and we can actually optimize that all the way out. Now, in my opinion, the basic thing you should keep out of this video is that if you can use the true for all method, use that. It will be optimized for the thing you are using, specifically in this case, the list. And if you can't, of course, and you don't know the exact implementation type, of course, use all. Now, it would be nice if all could actually detect the underlying type behind the scenes and optimize for the one. For example, if our enumerable is an array, use true for all in the array, or if the enumerable is a list, use the true for all for that list. That would be neat. I don't know why they haven't done it, but I want to know your thoughts in the comments as well. Let me know what you think about all this and leave a comment down below. Well, that's all I have for you for this video. Thank you very much for watching, and as always, keep coding.